The topic which we are going to discuss today is from quantum mechanics. We are going to study about a system where we are keeping a particle inside a one-dimensional potential box. Or you can tell, instead of box, it's somewhere in some textbooks we also tell it as well. When we say a particle, here we are considering a microscopic particle, and in our problem we will be considering an electron. So, let me draw the potential box. So, this is our potential box where we have two walls, and on the walls and after that the potential V is equal to infinity. Inside the well we consider the potential as equal to constant. Here we take it as V is equal to 0. The length of the potential box is L. Here we start with x is equal to 0 and we end up at x is equal to L. We are keeping an electron where this electron is allowed to move inside the well, and the energy of the electron inside the well, it is a constant. We have studied the Schrodinger's equation in our last classes, the Schrodinger's time dependent and time independent equations. This is an application of Schrodinger's time independent equation. So, let me start with the three-dimensional equation of Schrodinger, which you have already learnt. Del square psi plus 2m by h cross square E minus V psi is equal to 0. This equation we have to modify according to our system. Here we have, I have already told you that you are having only the single dimension, that is the x direction. Therefore, this del square, it gets converted to d square psi by dx square plus 2m by h cross square E. Here already we know that inside the well where the particle is present, we have got V is equal to 0. Therefore, this V will be equal to 0, psi is equal to 0. So, this is the equation by which we are going to solve this system. Now, when I was studying my quantum mechanics, or when I was in the earlier college days, when I studied this potential well, I used to wonder, actually when you view this potential well, it is having a y-axis and an x-axis, isn't it? Then why is it called a one-dimensional potential well? I used to wonder, but I was wrong. Thing is that here the particle is only allowed to move in the x direction. It is not allowed to move in the y direction. Therefore, it is known as a one-dimensional potential well. Okay. To begin with, we will simplify this equation by making this part equal to k square. So, I will write it somewhere here, that is our k square is equal to 2m by h cross square E. So, this is the substitution we are making, and it is del square psi by dx square plus 2m E psi is equal to 0. It has now become equal to d square psi by dx square plus x square psi is equal to 0. Now, to solve this, you are assuming the wave function. The wave function which we have taken here is psi is equal to a sin kx plus b cos kx. You can take any value, like any trigonometric value, like you can start with psi is equal to a sin kx or something like that. Like it can be a sine term, it can be a cos term, or you can combine the sine and cos term. Now, to solve this, you are applying the boundary conditions. Now, what is the boundary condition? Now when you look at the well, you are having x is equal to 0 and x is equal to L. This is the only two values of x which we know, that is x is equal to 0 and L. Now at x is equal to 0, we know that potential V is equal to infinity, and also at x is equal to L, the potential V is equal to infinity. So whenever the potential V is equal to infinity, the particle cannot be present there. That means if the particle is not there, automatically the value of psi will be equal to 0. Understood? And also it can be related to the uncertainty principle, because when the potential is infinity, you know that the particle's position is finite. You can measure the particle's position, and that is not according to uncertainty principle. Therefore, the particle cannot be present on the walls or wherever the V is equal to infinity. So we are taking the boundary conditions, that is boundary conditions. We will be applying the boundary conditions. The first one is when x is equal to 0, you have psi is equal to 0, and the second one is when x is equal to L, you have psi is equal to 0. So substituting in this equation, you get psi is 0 is equal to A sin 0 plus B cos 0. You already know that the value of sin 0 is equal to 0, therefore this term will get cancelled. You will only have B cos 0, where cos 0 is equal to 1. Therefore, the only thing which is remaining is B is equal to 0. So you get the value of the first constant, that is B is equal to 0. Now applying the second equation, you get psi, again it is 0, is equal to A sin KL plus B cos KL, but already you know the value of B is equal to 0, therefore you need not take that term. Now for this equation to become 0, either A should be equal to 0 or sin KL should be equal to 0. Now you cannot have two constants in an equation equal to 0. Therefore already you have B equal to 0, you cannot take A is equal to 0. Therefore obviously A is not equal to 0. So the remaining thing for this equation for the LHS and RHS to satisfy, you have got sin KL is equal to 0, and for making for getting the values of sin KL equal to 0, you know that KL should be integral multiples of pi. KL should be integral multiples of pi, where n is equal to 1, 2, 3, etc. Therefore, you get the value of K as K is equal to n pi by L. So substituting again into this equation, what you will get? You will get the value of psi and psi, because you are having an integers, psi is equal to 1, n is equal to 1, 2, 3, etc. You can take it as psi n. So I will write it here, the value of psi n, our wave function, which becomes, after substituting all the boundary conditions, you get the value of psi n as equal to, you get A, you have your sine term, sine k L. Because you are generalizing it, you should not take L, you should take x itself, but for the value of k, you substitute it as n pi by L. So this is the value of our wave function. So we have got the wave function as psi n is equal to A sine n pi x by L. Is it complete? No, it is not complete, because you are having a constant A. You have to find out the value of this constant A. To find the value of this constant, you have to normalize this function. You have already studied the normalization condition, that is for a three-dimensional system, that is triple integral psi star psi d tau is equal to 1. Here d tau is the volume element, psi star is the complex conjugate, and psi is the wave function. Now, according to our system, we will have only single integral. We will have only a single integral because you have got only a single direction, that is x. So, our equation will be integral psi star psi dx is equal to 1 with the limits of x starting from 0 to L. Now, you have to substitute the value of psi star psi in this. You already know that the value of psi is a sine n pi x by L, where we do not have a ith term. Therefore, psi star and psi will be the same. Therefore, you can just square and substitute it. It will become 0 to L psi star, that is a square sine square n pi x divided by L dx is equal to 1. Now, why do you keep 1? Because sure that the particle is inside the well. Now, since a is a constant, you take it outside. So, this becomes a square integral 0 to L sine square n pi x divided by L dx is equal to 1. You have to integrate it. You already know that sine square theta, when you are using it, when you are finding sine square theta, you can also substitute instead of sine square theta as 1 minus cos 2 theta divided by 2. So, this I am going to change it into that form. I will write it as a square integral from 0 to L 1 minus cos 2 n pi x by L, the whole divided by 2, that 2, since it is a constant, I am taking it out, dx is equal to 1. So, we will get a square by 2. On integrating, you will get it as x minus sine 2 n pi x divided by L by 2 n pi x divided by L with the limits 0 to L. This will be equal to 1. Now, when you are applying the limits, this x will be equal to L. Therefore, here you will have sine 2 n pi, that is equal to 0. So, when you are substituting the value of L, that term becomes equal to 0. Next limit, if you are applying, that is x is equal to 0, that also will lead to sine 0, and therefore, this term as a whole, it will disappear. So, the only term which is remaining, you have a square by 2 x from 0 to L is equal to 1, and this becomes a square by 2 L is equal to 1, or you get the value of a as equal to root of 2 divided by L. So, this value of a you are substituting in this equation, and you get the value of psi as psi n is equal to root of 2 by L sine n pi x divided by L, where you have got the value of n is equal to 0, 1, sorry, it is not 0, you do not take 0 here, I will explain why you do not take 0 there here, it is 1, 2, 3, etc. Now, usually when we take integers, when you substitute, you take the value of 0 also. So, here you do not consider 0. The reason is that if you are considering 0, this sine term will become 0 and the wave function automatically it reduces to 0, and that is not possible. So, wherever the particle is present, the wave function should be there, wave function cannot be equal to 0. Therefore, you have to start taking the value of n is equal to 1, 2, 3, etc. Further on, when you learn harmonic oscillators and all, there you take the value of n is equal to 0 also. You get the 0 point energy, you will learn later on. Therefore, in this, when you are considering particle in a box problem, here you don't take the value of n as equal to 0. Okay, so fine, you got the value of wave function. Now, this is not over. Now, next you have to calculate the value of energy. Now, from where you calculate the value of energy? From the first assumption which you took. Okay, that is k square is equal to 2m by h cross square E. From this equation, you get the value of energy. Now, k you already know it is n k square, you can write it as k is equal to n pi by L. So, n square pi square by L square, this is equal to 2m by. Now, here you are having an h cross. What is h cross? H cross is equal to h divided by 2 pi. So, instead of h cross, I am writing h divided by 2 pi. Therefore, it becomes h square into 4 pi square E. Pi square and pi square gets cancelled. You get the value of E as equal to n square h square by 8ml square, where here also you have got the value of n is equal to 1, 2, 3, etc. So, these are the two values you get solved for this system, that is the value of the wave function and the value of energy. So, we solve the system of particle in a one-dimensional box. We got the value of psi n as psi n is equal to root of 2 by L sin n pi x divided by L, and the value of En is equal to n square h square by 8ml square, where n is equal to from 1, 2, 3, etc. Next, we are plotting this value of psi n with respect to L and also psi n square, where psi n square, where psi n gives you the wave function, psi n square gives you the probability of finding the particle. We can just have a look. So, psi n, when n is equal to 1, n is equal to 2 and n is equal to 3, you got the variations as this one. Here you can understand that psi n is taking both positive and negative values. When we go to the psi n square, you can see that it takes only the positive value and it gives you the probability of finding the particle where this electron which we had kept inside the box is present. Another notable thing which you can find here, which is a difference from classical mechanics, is that the energy values are discrete. When you take n is equal to 1, you get an even value. When you get n is equal to 2, you get E2 value. When you take n is equal to 3, you get an E3 value. There are no energy levels between E1 and E2, E2 and E3, E3 and E4 and so on. Okay. So, this is the peculiarity of quantum mechanics. You get the discrete energy levels. Another notable thing is that when you look into E1, that is if you take L by 2, the probability of finding the particle in the energy level E2, it is maximum at L by 2. Now, when you jump to N2, that is n is equal to 2 level, that is E2 level, you just see where we could find the particle at E1 level, there is no particle there. So here the probability changes. So when it is E2, the probability, the maximum probability of finding the particle is at these two positions. So according to the energy levels, the probability of finding the particle also changes. That is the beauty. Another beauty of quantum mechanics is that you are taking a box. Okay, just imagine that you are taking a box. You are keeping a stone inside the box. That stone will be, wherever you place it, it is our choice. That is, you can keep the stone at right end, or you can keep it in the left end, or wherever you want it. So, and like if no one else, or if your friend doesn't take the stone out of that box, it remains there. Or if there is no external force acting on that stone remains there. If you come and look at it after 1 hour also. But you just see the beauty of quantum mechanics. Here if you have kept a particle there, and you have to find the probability. You have to see, you just see when it is at E1, you cannot find the particle at the ends. The maximum probability of finding it is at the middle. Okay, and when it comes to E2, it changes. So the particle behaves in a different way when it is coming to quantum mechanics, and that is the beauty of learning quantum mechanics. Thank you.